Okay, this is class number 22, and this is for compound interest, which goes with section 10.3 in your textbook. All right, our daily summary. In this lesson, we're going to investigate compound interest and the concept of annual percentage yield, or APY for short. And we'll just start off with a quote. The most powerful force in the universe is compound interest. And that was Albert Einstein. All right, in our demo today, just start with a quick reminder that under simple interest, only the principal generates interest. So our formula was that your future value, and that's what F stood for, was equal to your present value or principal times 1 plus, and right here we had our interest rate, which has to be written in decimal form for this, and T was the number of years. And again, our interest rate was APR, so it was annual percentage rate. So we had to have those match. And by the way, this simple interest is similar to the linear growth that we saw before the last test. So if you think back to linear growth, remember that had the form that the nth value in your population was equal to the initial one plus n times your common difference. If we do a quick example of this, and we'll do that as a review, let's say that your principal is $5,000 and your interest rate is 6%, so 0.06. Then this formula becomes future value equals 5,000 times 1 plus 0.06 times t. So we're just going to do it for how much it's worth t years from now. So the future value would be 5,000. So I'm going to distribute the 5,000. We saw a little bit about this in the last class. Plus 5,000 times 0.06 times t. And simplifying a little bit further, we get that the future value is going to be $5,000. Again, that initial value, your present value, plus 300t. So here's our common difference. But you're going to get $300 interest every year you leave that money in the account to grow. So that's our common difference. This is our initial value. And so simple interest is really linear growth. All right, number 2, under compound interest, not only does the principal generate interest, but so does the previously accumulated interest. So money invested using compound interest grows much faster than money invested using simple interest. All right, so number 3, let's look at an example. So imagine that your parents invested $5,000 at 6% APR, or annual percentage rate, in an account earning compound interest on the day you were born. Calculate how much money the investment is worth 1 year later. Well, 1 year later, you're going to have that original $5,000 times 1.06. So we know it's going to go up, so we're just using our percent increase formula. And grab a calculator so you can verify this. So that's going to give you $5,300 after 1 year. All right, 2 years later, both the $5,000 and the $300 interest you had are going to give you, it's going to be your present value. So we're going to multiply that by 1.06, and that's going to give us a total of 5,618. Okay. All right, so I want you to notice one thing. This $5,300 came from doing this calculation above. So I'm just going to write our calculation in one additional way. So I'm going to replace $5,300, or sorry, 5,000. No, $5,300 with 5,000 times 1.06. And notice that we just multiplied that by 1.06 a second time. So press pause, try that out on your calculator, make sure it gives you the same answer. All right, 3 years later, well, we can take the previous year's amount, $5,618, and again times it by 1.06. Because again, both the original amount and the new interest is going to earn interest again. So with a calculator, you can verify that this is going to be $5,955.08. But again, we're going to replace something here. We're going to look at where that $5,618 came from. That's from right here. So I'm going to replace that. So that came from doing 5,000 times 1.06 for the first year, times 1.06 for the second year, And now we've got 1.06 again for the third year. And so what we should start to see is a bit of a pattern. Okay, so let's try it one more time just to make sure. All right, so 4 years later, we should be able to take that amount from 3 years. So $5,955.08. That's our new principal or new present value. It's going to get 6% interest for the next year. And so that's going to give us a total of $6,312.38. And again, I'm leaving it up to you to press pause and try these out on your own. Right, but one more time, watch where this came from, or think about where this came from. That came from this calculation right above. So if I replace it, we can do this one last time. I multiplied it by 1.06 for the first year, again for the second year, again for the third year, and then one more time for the fourth year. And that's where our $6,312, or sorry, $6,312.38 came from. All right, so that means T years later, since we don't have a specific number here, we now have a pattern. Right, more specifically, if you go back in and count, if we let this grow for 4 years, we had to multiply by 1.06 4 times. So we could simplify this expression by using an exponent. In fact, we could do that for 3 years later as well. We could say that we used that factor of 1.06 3 times. And for 2 years later, we did it twice. So we used that factor twice. And for 1 year of growth, we just did it once. Right? So T years later means we're going to take 5,000 times it by 1.06 to the power of T, or T is your power. And this is what is referred to as exponential growth. This is a quick detour to what you did in the previous class. So remember that we talked about geometric growth long ago, or maybe not so long ago, it may just feel like a long time. Right? In geometric growth, remember that we found the nth value in the population by taking the initial value, multiplying it by a common ratio, and using that common ratio a total of n times. So if we look, here's our common ratio. That's for 1.06, and here's our initial value. And this is an example of exponential growth. Okay, number 4, to get a general formula for annual compounding, take the formula we generated in the previous problem and replace $5,000 by a generic principal amount P, and change the 0.06 to a generic interest rate. And we're going to use the decimal form, and we're going to represent that by R. So your annual compounding formula for the future value F of P dollars is going to be given by the formula where we have F equal to P times 1 plus your interest rate for T years. All right, so let's use that down below. All right, number 5, you have $875 in savings that you want to invest. Your goal is to have $2,000 saved in 7.5 years. Your local bank is offering a CD that pays an annual percentage rate, or APR, of 6.75% compounded annually. And so what is the future value of your $875 in 7.5 years? Remember that this is an annual percentage rate, which means interest is credited only at the end of the year. So we can't use 7.5 years. Unfortunately, we can only use 7 years. So we're not following the rules for rounding. We're actually just rounding down. Again, interest isn't credited till the end of the year, or calculated to the end of the year. All right, so looking at this formula, we're looking for future value. So we're going to leave F in our formula. Our principal or present value is $875. Our interest rate is 6.75%. So that is 0.0675 in decimal form. And that's going to grow for 7 years. So again, grab a calculator, try this out. Press pause if you need to. You should get an answer of $1,382.24. Okay, , 'All right, 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 Okay, part B, if you're short of your $2,000 target, how much more would you need to invest to meet the target? All right, so here's our formula again. And notice in this case, we have our future value. We've got our target. So we're going to replace F with $2,000. But now we want to know how much we would need to invest. So we need to know what the P is. So we're going to leave P in our equation. Still the same interest rate. And we're still going to let it grow for 7 years. All right, so solving for P, and this is where you want to get in the habit of trying to do all of this at once on your calculator. So I'm going to write it out the way you would do that. We're going to divide both sides by 1 plus 0.0675 to the 7th power. And that'll give us our present value, or the principal. So that should give us an answer of $1,266.06. If you're off by a little bit in here, double check that you're being exact up here. And again, the goal is to be able to type that in all at one step. Okay, number 6, you have $875 in savings that you want to invest. Your goal again is to have $2,000 saved in 7.5 years. Your local bank is offering a CD that pays an annual percentage rate of 6 3/4%, compounded monthly. So before it was compounded annually. So in this case, the bank is offering to pay you part of your yearly interest each month. So you're going to get more money sooner, and your interest should earn more interest. Plus, you'll make interest on that half year you didn't get anything for in number 5. So what is our future value going to be in 7.5 years? Well, our future value is going to be $875 times 1 plus, and again, our interest rate, we're not going to get it every single time, but we're going to get a fraction of it. So if we get it spread out over 12 months, we'll get a 1/12 of it each time. And if it's done every month, that means it's going to be done a total of, let's see, there's 12 months per year. 12 times 7.5 years would give us 90 times, or 90 months during that time span. So up here, we're going to have 90 as our exponent. So it's telling us how many times the interest gets credited. So our future value then is going to be 875 times 1 plus, and here if you get an exact decimal, you can make that change. So if you carry out that division, you'll get 0.005625 to the 90th power. And if we type this in all at once on your calculators, or maybe in 2 steps, if you do this as 1 step and then multiply by 875, that's also okay. You're going to get a future value of $1,449.62. And so again, the key was this was done monthly, which meant that you only get part of your interest rate each month. You get a 1/12 of it each time you get interest credited. But as a result, the interest is going to be credited more times. It's done each month, so we need to figure out how many months there are during that time period. Oops. All right, so part B, will you have $2,000 in 7.5 years? Unfortunately, no. But note, if you go back to the previous page, we do have more money than we would if we didn't do compound interest spread out over 12 months or compounded monthly. So more money than we had when we did compounded annually. So again, compounding monthly gave us a little bit more money than when we compounded annually. And compounded annually, if you flip back to double check this, we found that you got $1,382.24. So I should put a but here. We didn't get the $2,000, but we did get more than we did before. All right, so number 7, what if we do this daily? Well, if we do it daily, then your interest rate is going to be split into 365 pieces. So we're going to have 875 times 1 plus. Here's that interest rate, split into 365 pieces. So you get a fraction of it each day. And then we've got to figure out how many days there are over that 7.5 year period. So assume there are 365 days per year, times that by 7.5 years. And we're going to get 2,735.5 days. And just like we saw before, we're not going to be able to use that extra half day. So we're going to have to take that out and put 2,735 up here. And again, that's because interest isn't credited till the end of the day. So that extra half day, it hasn't been done yet. All right, so our future value is going to end up at $1,451.48. And I'll leave it up to you to double check this on your calculator. And if you can, try and type that all in one command. So that means you're not hitting equal at any point in the middle. You just wait until the end for that. All right, so in general, number 8, the general compounding formula, future value F of P dollars in T years and an annual percentage rate of R%, compounded N times per year, is given by this formula. So again, here's our future value. Here's that principal or present value. Here's that interest rate split up. So again, if you're doing it monthly, for instance, N would be 12. So you get a 12th of it each time they give you interest. If you're doing it daily, then N would be 365. And you can think of N times T as the total number of compoundings. Okay, one other note in here, because you might see this in your homework, but R over N sometimes is given the variable lowercase p, and that's referred to as a periodic interest rate. That's what's the interest you earn each period. And another slight difference you might see in other textbooks, N times T and the total number of compoundings. Sometimes other texts or other formulas put a capital T in there instead. Right, so in that case, you might see the formula written out as F equal to P times 1 plus lowercase p, and then a capital T in your exponent. And again, you may see this in our textbook, or if you're using those help features in MyMathLab. Either way, though, remember that the formula sheet we have, let me see if I can find that. Formula sheet, which should be somewhere in your packet. Here's the formula we just worked with. And by the way, here's the simple interest formula we worked with in the previous class. So we've written out in a little bit more detail. And if you forget what all those pieces are, you can find them down here. So for instance, T is the time in years, N is the number of compoundings per year, or number of payments per year. And there's your reminder about periodic interest rate as well. Okay, so one of the remarkable properties of compound interest is that even as we let the number of compoundings increase without bound, the future value F approaches a limiting value, which is only so big it's going to get. So even if the money were compounded 1 billion times per second, the future value would still not be more than this limiting value. This limiting value represents the future value of an investment under continuous compounding. So continuous compounding means an infinite number of compoundings occur each year. And so our formula for that, we've got our future value, just like before, for P dollars. So that's your principal or present value. And we've got E here, it's a constant, and it's approximately equal to 2.71828. If you type that into your calculator, if your way to find that on your calculator, you're going to actually, there's more digits after that 8, but we're going to use just the first 5 digits. Got our interest rate and the number of years both in our exponent. So R, again, is your interest rate, should be put in decimal form for this formula to work. So keep in mind that E. So the derivation of this formula and the magical appearance of E requires some calculus. So instead of going that route, we're just going to accept it on faith for now. We're just going to learn how to use the formula. All right, so the question below that, how much is your $875 and an APR of 6 3/4% compounded continuously going to be worth in 7.5 years? So using this formula, there's our present value, E, and then our exponent, here's our interest rate, times 7.5 years. And now we can use that half year because if it's being done continuously, anytime we want to check for its amount, we can do that. So our future value, and again, double check this, it's $1,451.68. That's the biggest amount we can get with compounding. So even if we compound continuously every single instant, this is the most money we're going to end up with. That's our future value. All right, and the last thing here, number 10, the annual percentage yield, or APY, of an investment, which is sometimes called the effective rate, is the percentage of profit that the investment generates in a one-year period. So again, annual is where we get the one-year period. And percentage means we're going to report it in percent form. And yield is the money that comes in. So that's the generating piece. How much money did you generate? What's your yield? All right, so for an example, if you start with $1,000 and after 1 year you have $1,099.6, what is your APY on your investment? What's your annual percentage yield? So we can use our percent increase and decrease or percent change formula. So if we take 1,099.60 and subtract the original amount or principal that you put in, we're going to find that you earned $99.60. So you can think of this as your yield. But now we want to think about it in percent form. So we're going to take that change, that increase, and divide it by the amount you started with. And that's going to give us 0.0996 or 9.96% for our annual percentage yield. All right, one other way to think about this, so just giving you another option. Let's think back to that formula we had earlier. So if we put in our future value for F and our present value in for P, and leave R blank for now, T is going to be 1 because we're looking for 1 year. If we solve this for R, we're going to find that R is equal to the same answer that we got above. So here's another way to handle that problem if you'd like.